so ions. What do we know about ions? Just throw things out there. We've talked about them extensively. Anions, cations. Good. Anions, what kind of charge? Negative. Anions. Cations are positive. Good. So reviewing here, we start with valence electrons because valence electrons are the ones responsible for making ions, whether it's a cation or an anion. A valence electron are the electrons that are in the highest occupied energy level. And they're responsible for giving elements their chemical properties. So it doesn't really matter how many electrons they have. What matters is how many electrons are in that outer orbital. So looking at the table, we need to figure out how many valence electrons are in each of these configurations. So to review, looking at lithium's configuration, you need to identify the highest energy level. So either this number 1 or this number 2. Which one would be the highest energy level? 2. The trick here is which number is bigger, 1 or 2? 2 is bigger. So we look at the number of electrons dealing with 2. And so the number of valence electrons here is 1. How about beryllium? We look for the highest energy level. Again, it's looking like 2. And then we look at how many electrons are in that energy level. And it is 2. All right, nitrogen. We have a 1, 2, and a 2. What's the highest number? 2. So this time we have 2 2s. That means you have to look at the electrons in both of them and add it together. So nitrogen has how many valence electrons? 5. And then neon, same thing. We have 2 second energy levels. And so we have to add the total, or add the 2 number electrons together. 2 plus 6 is 8. So valence electrons for the S and P blocks. If you remember, the S block will follow the group number. So if it's in this first group, there will be 1 valence electron. In the second group, there is 2 valence electron. In the P block, so that's starting over with boron, carbon, nitrogen, oxygen, fluorine, and the neon. It follows this formula. It is the group number minus 10. So if we're in group 13, minus 10, and we will have 3 valence electrons in all of those elements. Brett? Pondering.
1, 2, 3, 4, 6, 7, 8.
Yes. Or you can just count straight across, skipping the transition metals. Then it would go 3 valence electrons, 4, 5, 6, 7, and 8.
Did we have a question about that on the ASVAB test? Something about electrons.
Okay, very good. So scientists like to draw things, maybe not the most artistic way, however. So they use an electron dot diagram to show the valence electrons of an atom. They show them as dots distributed around an element symbol. So in group 1, we said we had 1 valence electron. So lithium they picked as the example element. And so they write the symbol and then 1 dot to represent the 1 valence electron. Group 2, they picked beryllium as the example element. There's 2 valence electrons, and so there are 2 dots. The important thing to notice here is that the dots are as far away from each other as possible. Okay? And this is because like charges repel. So they will situate themselves as far away from each other as possible. Looking at boron here for group 13, this would have 3 valence electrons. And so they put the 3 valence electrons. A way to, they're always going to be like a square is around the symbol. And so 1, 2, 3, 4, they don't ever put them on like the diagonals. Okay? So always on one of the square sides. Carbon has 4. And then notice here with nitrogen, once we have 5, we've completed 1 electron on each side, and now we begin to double up. This would be kind of representative of whose rule was it when we did Hund's rule, electron filling. So now we can double up once each side has 1 valence electron placed. Does that make sense? The maximum for now, there is an exception to this rule, is 8 valence electrons, and so this is what a complete valence set would look like. Noble gases, we should know by now, are very unreactive because they have a complete electron configuration, a complete valence shell. This is where you have 8 valence electrons is the goal here. However, the exception to 8 valence electrons is what element? Helium. Its valence electrons are full at 2. So scientists have come up with this octet rule, and that states that elements tend to form compounds in ways that gives each atom 8 valence electrons. This is elements' desire to have a noble gas configuration. So in order to achieve the octet rule, you can either share your valence electrons or you can completely transfer your electrons. So metals will tend to lose valence electrons and nonmetals tend to gain them. Cations, like we talked about at the beginning, these are positive ions. And they become positive because they lose their valence electrons. This means that there are more protons than electrons. An isoelectronic describes 2 atoms or ions that end up having the same electron configuration. So once we either gain or lose electrons, this creates an electron configuration that will look very similar to a full atom. And so magnesium and aluminum are examples here. Without them becoming ions, that is their electron configuration. But when magnesium loses these 2 valence electrons, it now becomes 1s2, 2s2, 2p6, which is the same electron configuration when aluminum loses its 3 valence electrons. So then these 2 would become, or are as known as, isoelectronic ions. So Logan's asking a good question. He's asking if even though these are isoelectronic, if they're still 2 distinct elements, and they are, because it is the number of protons that determines an element's identity. So magnesium here is still having, is it 12 protons? There's still 12 protons here, which makes it magnesium. It gives its identity. Aluminum still has the 13 protons, which makes it aluminum. Even though their electron configurations show them as being the same, it's only the same in terms of the electrons, not the protons. Another way that you can show a cation is with the dots. And this just shows the loss of that electron. This is dot, then becomes written as a single electron.
That has nothing to do with that other dot thing that we were talking about.
It kind of does. This is the dot diagram for sodium because there's 1 valence electron, and it's showing the removal of that electron to a free electron, so to speak. Okay. And this plus is showing that sodium is now a cation instead of a full atom. Anions are then the opposite in that they are negative ions. That means they are gaining electrons. Again, this diagram here is showing you isoelectronics because they end up having the same electron configuration. This chart again just shows you your valence electrons and the charges that are associated with them as they either lose or gain electrons. If you notice, they are the same for each of the families or groups. Transition metals are the exceptions here. We kind of talked about that last chapter. They are located in the D block and they can hold up to 10 electrons. It's hard to lose enough of these 10 electrons to achieve noble gas configuration. So what ends up happening is we often lose these S block electrons because if you remember Aufbau's filling chart fills the 4s before the 3d level. And so those 4s electrons or 5s2 electrons will get removed first. Many transition metals will have multiple ions, each with different charges, and we got introduced to that last chapter. So, remember, according to Aufbau, the electrons fill the 4s before the 3d. The s electrons are always the first to be removed when forming ions. The charge then makes 2 plus, very common because there's 2 electrons in that 4s level. So we can remove or add electrons to the D sublevel. However, it's slightly challenging. If we have a half-filled D sublevel, so that would mean D5, so there's 5 electrons, that's particularly a stable configuration. So if an element has D5, in its electron configuration, it's not really likely to gain or lose electrons. That's not to say it can't, but it's unlikely because it's pretty stable. If a transition metal has very few electrons, like, is it scandium, or did I write the right one? Yes, element 21, it may be able to achieve noble gas configuration because it has only 1 electron in that D sublevel. So that could be fairly easy for that single electron to be removed. And then zinc and copper may be able to achieve a full D sublevel and kind of get a pseudo noble gas configuration is what this is called. I'm not too concerned that you know that term. If it gets a pseudo-noble gas configuration, it's referred to as that because it gets that full D sublevel. It is a fairly stable configuration.